Measured against public tests it is allowed to see, the success rate hits 96.64%. But against hidden private tests, performance abruptly stalls at 47.90%. We evaluate automated systems by watching them succeed at visible tasks, but their actual stability is often defined by unseen constraints. The SWE-bench Science benchmark tests this exact boundary in modern software engineering. It evaluates AI coding agents against 119 repository-level tasks, pulled from 98 GitHub repositories across 20 scientific domains. The researchers tested multiple models and agent configurations to establish a baseline. The leading performer was the Claude Code harness running Anthropic's Opus 5 model. This chart shows the evaluation metrics for that top configuration. This is measured as pass at 1. It is a binary all-or-nothing metric. If a single private test fails, the agent scores a 0. To ensure isolation, these private tests are architecturally separated from the agent. They are mounted in a distinct evaluator container only after patch submission. The green checkmark from a standard visible test suite is now a quantified false comfort for scientific code. To accurately measure an agent's capability, the first thing a lab must build is a hidden validator set. To understand why more than half of these submissions are failing the private evaluation, we have to look at the internal logic of the code the agents produce. You might assume the models are simply writing bad code that causes broad system regressions, fixing one bug but breaking 3 others. The data rules that out. The pass-to-pass metric, which tracks whether previously passing private tests continue to pass, remains above 94.92% across all tested configurations. The agents are not breaking existing functionality. The actual behavioral flaw is that the agent fits its patch exclusively to the evidence it has shown, ignoring the broader scientific contract behind the software. The authors categorize this specific mechanism as the incomplete fix. This network visualizes a software architecture. When an agent receives an issue prompt, it targets the isolated module and perfectly patches the visible symptom, but it leaves the surrounding system untouched. Complex interactions, data flows, and shared invariants required by hidden validators are ignored. A standard continuous integration pipeline will pass this incomplete fix because it relies on the exact same public test the agent used to optimize its narrow patch. Before we examine how developers try to prompt their way out of this failure state, take a moment to subscribe to the channel. The current generation of coding agents act as symptom solvers, not system engineers. They optimize purely for the visible constraints of the test. The standard industry response to domain-specific failures is to inject the agent's prompt with dense scientific rationale, assuming that more context yields better code. The benchmark researchers tested this assumption with a 91-task ablation study, varying whether explicit scientific guidance was provided while preserving the repository context. This chart tracks pass-at-1 performance for models with and without added scientific rationale. We start with the stronger model, GPT 5.6 Sol, establishing a baseline of 36.26% without extra guidance. When researchers supplied the scientific rationale document, performance dropped, falling to 31.87%. Then they evaluated the weaker model, DeepSeek V4 Flash, starting at a lower baseline of 16.48%. Given the exact same rationale text, the weaker model's performance climbed to 23.08%. Running this ablation required immense compute. Injecting these rationale documents pushed the input token count to millions per task, between 3.7 and 7.4 million tokens. Supplying the domain knowledge made the stronger model more expensive and worse, while making the weaker model more expensive and better. The authors attribute the strong model's decline to anchoring. The detailed text caused premature reliance on the supplied explanation, constraining the agent's natural exploration of the repository. Scientific knowledge is not universally beneficial. Poorly aligned guidance restricts a capable model just as easily as it assists a weak one. We have to look past the findings to audit the experimental design itself, because the headline claims are built on several structural fragilities. This matrix shows how the benchmark assigned models to testing harnesses. Opus 5 is exclusively paired with Claude Code, and GPT 5.6 is exclusively run in Codex. Because no model was tested across multiple harnesses, it is impossible to separate the model's inherent intelligence from the tool executing it. The conclusion that Opus 5 is best is entirely confounded with the possibility that Claude Code is simply the better harness. The statistical strength of the top ranking is also fragile when quantified. This visualization represents the 119 tasks evaluated in the benchmark. The difference between Opus 5's first place, 47.90%, and GPT 5.6's second place, 46.22%, comes down to exactly 2 resolved tasks. The paper does not provide testing seeds, variance tracking, or confidence intervals. On a binary metric, a 2-task lead sits well within the margin of noise for any repeated run. The rigor of the rationale ablation study also requires scrutiny. The researchers tested the models at different parameter settings than the ones used for the main leaderboard. This resulted in net swings of just 4 and 6 tasks across the dataset. The authors explicitly state that these paired descriptive differences do not establish statistical significance or a causal effect. And the most critical omission in the ablation study is that the top-performing configuration, Opus 5 at maximum settings, was excluded entirely. The paper's most notable finding wasn't tested on its strongest agent. Finally, every task in this benchmark was rolled back from a real public repository. The schema logs a contamination tier, but the paper fails to report any per-tier scores or verify whether the models had already seen the correct fixes during their training phase. The introduction of a public-private split is an essential mechanism for evaluating software engineering, but builders must extract their own data and implement their own hidden validators rather than relying on unablated headline claims.